Hi, this is a video for COMP441 and 442 compiler design. This is for week 10. In this video, I'm going to present assignment number 5, final assignment of this project, which is about generating the code, the executable code. So let me show first where you go about in getting this assignment. It's here, week 10 handout. As for all other assignments, you get a zip file. Open the zip file and you get the handout in a PDF here, which we're going to cover in this video. And then you have example source files, which are mainly the same source files that we had previously. Note that as there are different ways you can actually generate the code, and I don't want you to think this would be the exact code to be generated. I'm not providing you with an output of the code. If you want to see excerpts of how the code should be output, please go to the last two videos for the course, Code Generation 1 and Code Generation 2. It gives you very extensive and precise description of what is it that should be generated. Okay, so let's go to the handout. So assignment 5, this is due on April 3rd. Again, 8% final grade. Here you have to do code generation. So essentially you build your AST in assignment number 3. In assignment number 4, you did your symbol table generation and semantic checking by traversing the tree, hopefully using the visitor pattern. If you did use the visitor pattern, what you'll have to do for assignment number 5 is just design another visitor that, as it will traverse the code, as it will traverse the AST, it will actually generate code. So it's about designing a new traversal of the AST, whose semantic actions are about generating code. One of the particular difficulties or difference with this assignment compared to the others is that you have to generate code. So you have to understand what is the nature of the language that you have to use to generate the code. So as I explained before, earlier in the course, let me go back to the web page here. So if you go to my web page at the bottom, the web page, you'll see Moon processor and simulator here. Let me just go to this here. So this is Moon machine. So this is a essentially this is a processor simulator. This was done, implemented by the late Peter Gogono, who used to be a prof in our department for a long time. This is a C program. You compile this C program. It is an executable. That's what you're going to generate an executable that actually reads a file in the Moon that is written, that is a program written in the Moon assembly language. So you're going to generate code in this Moon assembly language. And then this Moon processor is going to be able to execute this code. So if you want to execute your generated code on your own computer, take this moon.c here, compile it, and then it's going to generate an executable that you can, with which you can execute your generated code. Okay. There's some kind of essentially a virtual machine. Okay, so I'm not going to, in this video, explain what is the Moon assembly language. I would advise that you take some time to, because there's some documentation also about this here. The document that describes what is this Moon assembly language, how does this work, and so on and so forth. What are the instructions that you can have? Gives you some example. And then you can, my advice is that you sit down and read about this Moon language before you start. If you listen to the videos, you'll see that, of course you saw assembly language before, might be slightly different. The language, the Moon is likely to be a little bit different from what you learn in assembly before, but all assembly languages resemble one another. So take some time to read this documentation. Of course, listen to the videos. It's going to tell you very precise, again, instructions as to how to generate the code, and in particular, what is the code that you should be generating. Okay. So in this video here, I'm not going to present all of this, of course, but I'm just going to be presenting what you have to do. So what is it that you have to do? So first, you have to, well, one of the things that a executable code in this Moon programming language or assembly language is that you need to have variables that are stored or values that are manipulated by this program. So you need essentially to allocate memory for your variables in your source program. There is some variables that are being declared. So you need to figure out what is the size of memory block that you will need to create in order to use a variable of that kind. So, for example, for integers or floats, for arrays of integers or floats, for objects that have inheritance, for an array of object, so on and so forth. You have to determine what is the size of each of these values that you want to store in this and each of these variables that are being declared in your program. Now, one of the things is, as you may have seen also, let's go back to here, visitor for all phases. I suppose that you have seen that when you did assignment number 4. You may have seen there were 1 or 2 visitors that were actually for code generation. Okay, so I strongly advise that you look at this code also. So that's going to give you some very good hints as to how to generate the code, especially if you are using a visitor pattern. Please look at this here carefully if you want to have some example. One of the things that this visitor in the code that I just pointed to here, one of the things that it does is that it actually loops over the AST and then determines what is the size of each of the variables, the memory size that is necessary to actually store each of the variables, and then stores this as information in the symbol table. So you essentially have some kind of visitor that retraverses the tree and then computes what is the size in terms of bytes that is necessary to actually store each of the variables that are referred to in the entries in the table. Another thing that you will need eventually also is what is the size of a scope. For example, what is the size of a class, which is telling you what is the size of an object when you declare an object of this kind, what is the number of bytes that you need to reserve in memory in order to store an object of this kind. If for the functions, if you are using a stack operation to actually call a function, so that when you call a function, you create the stack frame on top of on the stack, an execution stack. So you need to know what is the size of the stack frame for this particular function, which is the addition of all the variables that have been declared inside of this scope. Okay. So that's why the totaling the amount of variables that are necessary to execute a function, namely all the variables that are declared in this scope, is also necessary to have, which you can also store in the symbol table. So you can have, as the example code shows, another visitor that simply retraverses the after you've generated the tables. You have another visitor that retraverses the tree and then determines what's the size of each of the variables that are declared in this program, plus what is the size of each of the scopes, so either the class scopes or the function scopes, and then stores this information in the table. Then you have the code generator itself, which is another phase, again, that will use this information in order to generate the code. So memory allocation is essentially two phases. You determine what is the size in terms of byte of each of the variables. Once you know that, then you can actually generate the code. Code generation for memory allocation is essentially that you have an assembly line that describes that reserves a block of memory. Please refer to the slides sets, the two last slides set code generation 1 and 2 in order to have more information on this. Okay, so this is for memory allocation. Other thing that's important about this assignment is that at the end, unfortunately, and also fortunately, there is quite an amount of students at the end that can generate some code, but cannot execute the code. Okay, so if you can't execute the code, that doesn't mean that you lose all the marks. Okay, so if you generate some code and it does not execute, at least the marker can see what code you're generating, and you'll receive partial marks for these. Okay. So if that's your case, then what you need to do is to pick and choose easy things that for which you can generate code to as to gather as more mark as possible. For example, here, determining the sizes of each of the variables and the sizes of the scopes, putting this in the symbol tables is an easy way to get easy marks for code generation. Then for, as you know, in this programming language, we have functions. For example, the main function is a function, okay? Or if you have other free functions or member functions. Member functions are a little bit tricky because the member functions can actually refer to the data members of their own class, okay? Which is a little bit more tricky to implement compared to free functions. So if you want to do functions, I would suggest that you start with a program that has only the main function and free functions. If you were able to do that, then maybe you can consider later to actually do member functions. Not that it's entirely different, but it is different if you want to allow a member function to access the data members of its own class. The calls to a member function is also a little bit more tricky because of that. So functions, so you need to essentially to branch to, so when you'll be executing the code for the main function, the assembly code for the main function, you'll basically, your assembly code will start at the beginning of the execution of the main function. Then when you call another function, let's say like a free function, then you're basically gonna branch to another part of the code, and then you're gonna continue executing here. Okay? Essentially, executing a function is calling an assembly subroutine. Okay? And then when you finish this other function, then you go back to where you were before the call to this function, and you continue executing, for example, the main function. So you branch to a subroutine, and then when you finish this subroutine, you branch back to the original function you were in. There is some very specific assembly and Moon assembly instructions that enable you to do that. Again, please listen to the videos or come to class about to have more information on this. Another thing that you may want to do is when you call a function is pass parameters. So if a function receives parameters, then you need to have some kind of mechanism to actually pass these values to the subroutine. Okay. So again, this is explain in details in the slide set for code generation 1 and code generation 2. Of course, also functions also return, some functions return a certain value. That means the value needs to be passed somehow to the calling function. So essentially, that's what you have to do for functions. Then, of course, inside your functions, you may have statements. So they have different, as we saw, there's different kinds of statements in this language. Assignment statement, conditional statement, loop statement, input-output statement, return statement, etc. So for each of these, it is explained in detail in the slide sets for code generation 1 and 2, how to generate code for each of these different kinds of statements. Then there is, well, if you want to access the values of your variables, then you basically are using either labels or offsets. So depending on if you're using a stack or if you're using labels, in the lecture videos and in the lecture time, I will explain these two different ways you can generate the code. I advise, if you want to be able to go as far as possible, that you actually use a stack operation mode. So when you call a function, there's a stack frame that is created. I'm showing in the videos how to do that pretty easily, okay, in a very simple manner. But if you don't want to use a stack, then you can use labels to refer to each of your variables, so that each of your variables in the program would be statically allocated as the program starts. So that would avoid that you use offsets to actually refer to each of your variables. That would be possible to not use offsets if you would not have aggregate data elements, such as, for example, when you have an array. So you can have a label that represents the first memory cell allocated to a variable. But if it is an array, then how do you access each of the different elements? You have to use offsets. You compute your offsets and then use the offsets at runtime. The same thing goes if you have objects. You have to compute offsets for each of the different members of an object. These offsets will actually be stored. If you look at the code and in the videos, that these offsets are actually for classes. The offsets are actually stored in the symbol table for that particular class. The assumption being that when you store an object that belongs to a class, that each of the data members of the class are stored in a contiguous memory block in the order in which they are declared in the class, such as what is happening, for example, in languages like C++. Then that's how you can actually determine what are the offsets to access each of the elements, which you cannot refer by name, but you refer to them by offset, which is the cumulative offset that you compute and store into the symbol table as you do the first phase, as I explained here, when you compute your size of each of the types, essentially, or variables that you want to, that you declare in your program. So as you determine the size of a class or an object of a class, you also store each of the different offsets for each of the different elements that are part of a class. So that's how you can actually somehow have your code to refer to a particular member of a class by using offsets. So you see that if you want to use, if you don't want to, because using offsets requires that you compute these offsets values, which makes it a little bit more complicated. So if you don't want to use offsets, there's a lot of things that you're not going to be able to do. Namely, you won't be able to use arrays, and you will not be able to use objects. So this is about number 4. So it's basically dealing with offsets for aggregate data elements. And then you also, of course, in statements, for example, like in an assignment statement, you have expressions. Like, for example, you have an assignment statement, you have x is equal to a plus b. So you need to generate the code for accessing a, accessing b, and then adding the value of a and b. One of the things is that every time you have a certain operator that is part of an expression, you need to compute the result of the application of this operator on these two operands, and you need to actually store the intermediate result of this particular operator. And if there are a sequence of operators being applied, like in a tree, as we have in the AST, then for each of the nodes, essentially, in the tree, you will need to have an intermediate result that you will have to store. I'm proposing that you do it in a very simple manner, that every time you have a certain operator, that you actually reserve an additional memory cell, or additional memory to actually store each of the sub-results. If you look in the code that I give in the visitor example, you will see that actually it is adding in the symbol table for each of the operators that are being called in an expression, it's adding a variable to store each of the intermediate results, which will then be reserved as memory cells by the assembly language as this function is executing. And then it's going to be able to store the intermediate result of the application of a certain operator in a memory cell, and then be able to continue the execution of an entire expression. Okay. So expressions are something that you may deem as should be very basic, but it's not necessarily very trivial. It's not super difficult, but it's not trivial. You see, as for assignment number 4, there's a lot of things that need to be done if you want to eventually be able to execute your code that has functions, that has classes, and so on. There's a lot of things to be done. So what I suggest is you start with simple things that are somehow easy to do, and you build incrementally, and you add more things. Yeah. Okay, so that's about it. What you need. So again, here's the description of this little document that I'm asking you. So as you see here, there is a table here that I'm showing you the things that need to be done. These are the marks that are associated with each of these. And then I could also put a color code here, which I'm going to explain later here. So in your section 1, essentially what I want you to do is to explain what are each of these items that you can actually do, that you have a code generation for. So having a table like this, and then showing me for each of your different code examples that you give, source code examples that you give, what is covered by each of these examples. As you will see in the assignment handout, is here. Yes. There is actually such a table in the examples, like this one here. Essentially, in your section number 1, I want to have a table like this. And then for each of your sample source files, you have a table like this that shows whether or not you're doing each of these things. Just to make sure that the marker has an easy way to see what is it that you actually did. Then let's go back to this here. So that's it for part number 1. And then part number 2, you describe your design. Hopefully you're going to be using the visitor. Then you describe what are the different phases, different visitors that you have implemented, so on and so forth. And section 3 is essentially use of tools. Then, okay, for implementation, here I put this color code here because very often students don't have either, things were not working in their previous assignments. There are things that you cannot do for some reason, or students don't have enough time. As you see, there is a lot of things that you could be generating code for, and I will give you partial marks for the code that you have generated, even though, if you want to, of course, generate code that you can execute, that means that there are a lot of things that are already done. So it's possible that you generate code, but if you use the Moon machine, the Moon machine would not be able to execute it because it's just bits and pieces of code that you have put in the file, right? So here, essentially, I'm giving you this color code. The red ones are things that you need to, if you want to be able to generate code, you need to implement these first. So for example, if you want to generate code and you want to demonstrate to the marker that your code works correctly, so you should be able to at least have an output, generate code for the output statement. That when you execute your Moon code, that, for example, if the code is supposed to compute certain values, then you can actually write these values so that they appear on the console, thus thereby demonstrating that the code is making the right calculation. Okay. So that's why I put this one in red here. These are important to have if you want to do a demonstration that your code works correctly. So there are things that, oh, sorry, retract my explanation here. Whether something is important to actually, for a demonstration, is whether there are lots of marks associated with it. So I've associated high number of marks or the basic things that you need to have in order to execute code correctly with the Moon machine. So anything that is worth like 2 marks, 2, 1.5, 1 here, these are things that are important to have if you want to somehow execute code. The red ones, the color code, the green, yellow, and red, are things that are more difficult. So you see that, well, particularly, that's what misled me here, that this one is worth 2 and is also red. Fact of the matter here is that for the input and output, it's not trivial to actually do it in the Moon code. There is a library file, as you will see in the, when you download the Moon machine zip file, you will see that there are actually libraries, like for example, lib.m or util.m. These are libraries of subroutines that have been written in the past by some students that I'm making available to you that you can actually reuse. And for example, if you go in lib.m, there is a subroutine that allows you to output something to the screen. The usage of these subroutines is somehow explained in the, I believe, in the Code Generation 2 lecture. Okay. So yeah, somehow it is somehow a basic feature to implement to be able to output something to the screen so that when you execute the code, that it actually outputs something which demonstrates that it is computing the correct result. If you don't have that, then in order to demonstrate that it correctly computes results, you will have to execute the Moon machine in debug mode and then show that it actually, some of the memory cells contain the right values, which is very tedious. So simple thing here is that you just you generate code for the right statement that outputs things to the console as you execute the Moon machine. Thereby, your execution is itself showing that it does the correct implementation, correct code generation. So you should aim to, yes, do these things that are of higher, worth more marks. And then if you want to aim for simple things, then you can aim for the green things. And then if you have more time or more capacity in terms of your implementation, do the yellow things and possibly the red things later. But especially for this one here, I strongly advise that you do this in the early stage, even though it's difficult. Okay, so that's about it for that. And then the only additional file that you need to generate in this assignment number 5 is the .moon code file that actually contains your Moon code. Okay. As always, and you have to design your own test cases for the code generation, and then provide a driver to easily demonstrate the assignment. That's about it for this assignment. Thank you.